this is just kind of an overview of what we've done over the past 3 years as we've rewired it. And then I've also got a link to, we created about a 30-page description, operational description, and troubleshooting guide. And it's available as a PDF, and I've got a link for that in here as well. So if you want to, you can get this presentation either with the QR code or this tiny URL, ACCRS wire. Either of those will get you this presentation and then the link to the PDF document. So you guys, probably most everyone here is familiar with the ACCRS Club. It's at the fairgrounds in Pleasanton, open during the fair, some good guys, train shows, mainly events that are on the fairgrounds. Really kind of restructured it to be very much great for the public to come in and see. The O-scale layout is a fairly large layout on one side. It has also an HO layout. If you look at the structure of the building, there are entrances on two ends into the building. On the right is kind of generally considered the front entrance. On the left is the back entrance. On one side, there's an HO layout, and on the other side is an O-scale layout. The O-scale layout is basically folded figure 8 with a crossover in the middle and a passenger yard and a freight yard. Overall, the layout's about 100 by 16 feet, 100 feet long by about 16 feet wide. So it's a fairly long and deep layout. And you can see where the dispatch panel is in the middle, which is where the original DCC control system was built into place as, a 2-cab, A-B cab DCC system. There are duct-through entrances to go into it. We have a lift bridge going into the back. The way it was originally built was by the way, very large curves, 90-inch minimum radius. It was built with 9 DC blocks on each main line, 2 return loops, and 2 yards. And so I actually have a couple of pictures here of the layout, kind of where they are, and different kind of pictures of how the layout looks. And I'm going to skip that because I think probably most everybody on this call has seen the layout at some point. But I thought I'd put those in there to kind of get an idea of how the layout is and how kind of long and skinny it is. So about 2005, somewhere in that time frame, they added NCE boosters to each cab with a simple double pull, double throw switch, separate switch for each cab. So that was kind of the first step, and you kind of see the control panel here. You can actually see there was a button that was a switch that was added over here to switch, but there are 2 switches to switch between DC and DCC. It turned out that created a fairly major decoder issue, because if you happen to be running your engine in DCC and someone threw a turnout and you switched into a DC block, it turns out DCC decoders don't really like being hit immediately with DC, and it tends to actually create lots of issues. And that, in fact, will damage most decoders. So one of the things we did about 4 years ago, maybe 5 or 6 years ago, was change to a single switch. So we kind of began a transition from DCC being an oddity to DCC being the normal mechanism. And as we used DCC more, though, another issue emerged. And that was that if you looked at the layout from the booster, which was wired right next to the central DC panel, the wire out to the farthest block, which was out there on the far left, actually was almost 100 feet of wire. And it turns out that DCC doesn't really like long wire runs. And it turns out in O-scale, that's actually magnified by the demands of current for the locomotives, because they have fairly high current demands. They can have 2 or 3 amp even outputs. We first started noticing this with some of our locomotives. For example, had an Atlas locomotive that had an Atlas factory decoder in it. Because we run for events that are, from noon in the morning to 11 o'clock at night kind of things that often are 10-hour running shifts, locomotives typically run for 2 or 3 hours at a time. What found was that with this Atlas locomotive, it would all of a sudden And it typically happened back in this corner. All of a sudden, the whistle would go off or the horn would go off, and it would not be able to be turned off. You could not turn it off from the DCC cab. The only way to resolve that issue, we found, was to take the locomotive upstairs, reset it back to factory settings, reload it from JMRI, and then it would be fine. Having been in electronics for a long time, typically that kind of thing is caused by a write bit error. So something was being written to memory. It was not written properly. It was written to the wrong place, and it turned the horn on, and the horn wouldn't go off. That's typically a factor that you've seen in data errors in transmission, and typically was happening after the locomotives were warm. This was exacerbated pretty dramatically about 2 years ago. Sunset, who makes a lot of the O-scale locomotives, went to lock sound decoders. And we had a couple of our members, that one who had bought a new Sunset locomotive, one that had a couple of Sunset locomotives converted actually by the guy who did the DCC decision work for Sunset. And he put in lock sound decoders. And what we found was all of a sudden these locomotives would be running on the layout and they would become zombies. And because by zombies, I mean they would literally run and there was no way to control them. You couldn't slow them down. You couldn't speed them up. You couldn't stop them. And it typically seemed to start happening back in this same place. So when David Gibbons was here, he actually brought his scope out and we started looking at the wiring and what we were seeing in DCC signals. So these are some pictures of the DCC signal on the wire that we were seeing with those lock sound decoders in that both in short blocks and the far blocks. So on the top, you see the DCC signal with no load. On the right, you see the lock sound decoder on a short DCC bus. Hang on. Sorry, I had to mute someone there. So if you look at the right, you see there's a lot of noise on the wire all of a sudden on that short DCC bus. And if you actually look at the timing between those spikes, that's actually the 40 kilohertz cycle of the PWM, the pulse width modulation circuitry for the motor. So, the way DCC decoders work is they're not like a DCC power or DC power supply where you change the voltage from 0 to 12. The way they work is they have 12 volts and they slice it back to 0 and then go back to 12 volts occasionally. In this case, it's about 40,000 times a second. So they turn on the power just for a short little bit. If the engine's going slow, they turn it on for longer if it's going fast, and then turn it on completely for the highest speed. The problem is what you see down at the bottom right, or bottom left, which is in that far block 9 with that 100-foot DCC bus, that noise that was being thrown out by the decoder is magnified dramatically by the inductance that's in the wire. And we ended up getting so much noise on that circuit that literally the decoder would lose what's called the I pattern to be able to read the data that was being transmitted on the DCC wire. And what the problem with it is once it lost that signal, even when it was moving and the PWM circuit was going and it got to what's on the upper right, it could no longer detect the actual data signal. So it literally would never detect another data signal. So what we realized very quickly was that this was a major problem. We really had to change things, and we had to get the system out closer, the power stations out closer to the blocks in the network. So we had some DCC goals as we set into this. We wanted to reduce DCC wiring to 30 feet from the booster with an absolute 40-foot maximum. We did not want any snubbers. We wanted to provide detector motherboard slots for up to 120 detector blocks per a 1961 SB-CTC plan one of our members put together. You actually see that on the next slide. We wanted to enable the 2 main lines and the associated sidings to be run in DC. So one of the things that happened was as more and more members had DCC locomotives, and members that had only DCC locomotives departed the club. What we realized was that DCC operation was becoming kind of the norm. But we still felt that having a DC operation as a fallback for shows, like for example, for the fair and other shows, as well as an opportunity for members to run locomotives before they did a DCC conversion to make sure they mechanically were sound, was a good idea. So basically we said, let's do just the main lines in DC. So all the sidings and yards would be DCC only. The main lines would be DC. And then all those other sidings and reverse loops should be unpowered when you put the layout in DC mode, because DC is literally just running trains around the Christmas tree. And the entire layout must be switched from DCC to DC together. We wanted to increase the overall capacity of the main lines. We only had 2 boosters that had caused some issues. So we wanted to go to additional boosters for longer trains and diesel lash-ups. The other thing we wanted was we wanted to have a single power on switch. We'd had that previously with an AC power on that powered on the equipment by the dispatch panel. So you had one AC switch, you could turn on the layout power, turn it off, and everything would go off. The problem we knew was that as we distributed the power systems, we sort of boosters out around the layout, they needed to be powered. If you powered them with a central 110, you'd have to run conduits out to those locations. So we decided what we wanted to do was use a 12-volt trigger signal that would actually be able to trigger all those stations to turn on and off without actually having 120-volt control. And then one of the other things was that having crawled under the layout, dealt with all those issues, said we should try to move all of our panels and all of this functionality to the edge of the aisle so it's easy to see, easy to work on. So that led us to a decision to plan for CTC. So this was actually, we started planning for CTC. We plan on using CMRI, and the club has acquired Chubb components and the New Jersey signals. We actually made a final buy from New Jersey signals just before they sold the company to Atlas, and we bought a lot of their O-scale inventory. And I think the deal he had with Atlas didn't account for the value of the inventory. So him selling that to us was all just cash in his pocket. So we actually got a great deal. So we actually have all the signals and all the CTC components we need to implement the plan that's shown here, which is actually a 1961 Southern Pacific CTC plan. One of the things that showed up was that increased from 28 to 128 or to 28 to 120 blocks. So our original DC layout had 28 blocks. When you go to this kind of a CTC plan, because of all the places you need detectors, for example, 2 turnouts and 2 tracks that previously in DC, or a main line, 2 turnouts in the siding that may have in the original plan been a single block, in a CTC plan becomes 4 blocks. So you go from 1 to 4. So basically what we said is, let's go ahead and put this together. We put in where some nodes could be for the CTC signaling. And that led us to a decision to put the boosters and the CTC equipment in really 3 locations. So the first location, and you kind of see these on the little plan up here, the main location is right inside the main aisle on the front. That covers this area in the front of the layout here. We then had another panel that's under a mountain of scenery back over here that covers this end of the layout, and another set of panels back in the back here that covers the back around here. You can kind of see how that's broken up here, up above. So at each of those locations, we needed to have 2 things. We needed to have what we called a power station, which would have the boosters and circuit breakers and other equipment in it, and then detector panels for the blocks. So this kind of shows where those were located. The power stations, 3 power stations, 1, 2, 3. And then there was a detector panel for power station 1. Power station 2 has detector panels here for most of the layout, but then has another little detector panel here for this area back in here. And then finally, we had a power station on this end with detector panels that covers this end of the layout. So each power station has boosters, circuit breakers, and then you'll see a DC to DCC relay. So this is basically what a power station looks like from the 120 volt side and the DC trigger wiring. So what you see on the left here is from the front panel, we have a DC switchover 12 volt trigger and a power trigger. Basically, the power trigger pulls in a relay, and that relay turns on 120 volt power into this power module from the wall. We also have a power selector switch that is a center off double pole toggle that lets you turn the panel on locally, turn it off so it can't get power, or turn it into what we call normal, which connects it to the relay so it can be turned on from the central panel. By the way, the 120 volt is actually wired to a wall outlet. So we treating these panels, even though you see they're made out of wood, they're enclosed and they're treated like an appliance. So if you want to work on them, what you do is just unplug them from the wall and remove the 110 volt power, and then you can work on them without worrying about getting hit by 110 volts. Basically, that 110 volt power then goes to a terminal strip, which feeds 2 transformers, 1 for each booster. We also feed a 30 amp DC power supply. By the way, if you haven't seen these are on Amazon. They're about 25 bucks, 27 bucks, something like that. Really nice to give you clean DC power for your layout. And then we put a panel fan in to keep things cool. The other thing we did is we found these relay boards. Each one of these is a single pole double throw relay. So basically each one of these has, 2 inputs and 1 output, and is a single pole. And those are ideal for switching blocks because the common side of the block can all be tied together. One side goes through these. So this relay allows us for each block to select either DC or DCC for that block. And that is actually controlled by, again, a trigger switch. And if you notice, all of these are tied together, so they all switch at the same time. So what it does is gives us a really easy way to switch everything from DCC to DC if we want to. By the way, stop me if there are any questions or comments as we go through this. Feel free. From a DC DCC wiring perspective, basically we have 2 boosters at the bottom of each of the panels. Those boosters feed in a cross fashion to 4 in 2 of the panels, 4, 1 only 3 PSX circuit breakers. Basically, these 2 circuit breakers, 1 and 2, feed in and become cab A and B, and in this case, this one also becomes cab B. So those are split between the boosters. So what happens is would be cab A and DC, which is one of the 2 main lines, is on one booster. The other one is on the other booster. That splits our load. So if you've got 2 trains in the same area, they're actually, if they're on 2 separate tracks, they're split between 2 boosters. The only time we have 2 trains or multiple trains on a booster is if they're on the same track, which is kind of the way the layout operates, fairly unlikely. Then those outputs of the circuit breakers feed into these the DCC relay board. Those are also fed by the cabs. So basically, each one of these becomes a block output, and actually there are the 2 sides of that. There's the positive and the negative, and those then feed into a toggle switch and an LED, and then there are outputs up here. These are those like Wago connectors. They're the clamp connectors, but these are nice because they have basically 2 poles on each connector, so you can have both sides of the wiring to the track off the connector. So essentially, by flipping this switch, we can go to DC. If we have a circuit breaker pop, it only impacts part of the layout. The other half of the layout continues to operate in that area. To support this, what we did was we did a distributed wiring system to distribute that 12 volt signal and the other things you need to run the layout. So basically, if you look at this, at power station 1 is where we have our DC command station. There's a command bus that runs from it And if you notice, that's this yellow. It runs yellow, runs over to power station 2, then runs over to power station 3.
Bill, it's Frank. Is all the wiring color coded?
Yes,
Great.
it's all color coded and it's all pretty well documented. So, um, and then we've got a bus. The thing about the bus and the trigger wires is they don't have to be serial sequential. So we actually, if you'll notice, we split those here. So, the trigger wires and the DC booster common go here and then go to each of these other 2 panels. So the idea here is at the front panel, you've got an on-off switch. You can flip that switch, turn on this part of the layout, and turn on all the control for the layout. And then there's a second switch you can turn on to switch the layout to DC. That will turn the main lines to DC and switch the rest of the layout off. So it makes it easy when you're operating the layout. So this is an example of the other thing we did. This is a pretty typical example of how people build model railroad wiring systems, and it's what I referred to as for lack of a better word, as single plane wiring. So everything is wired in a single plane, and you see all the components and you see all the wire. The challenge with this is grooming it, making it look good, managing it is a challenge. Plus, all of the electrical stuff, if you've got AC power, et cetera, is now exposed. So one of the things as we're laying this out, I had a memory back to when I was in college. I actually built if everybody remembers Dynaco, I built a Dynaco PAT4 stereo preamp and a stereo 80 preamp. Built them in my dorm room in college. So these were actually, you wired them with point-to-point wiring and stuff. But what impressed me about this, I thought back on it, was these were really nice looking units on the outside. But when you opened them up on the inside, you saw all the wiring. Well, the wiring could be nice. It didn't have to be perfect. You didn't have to worry about laying it out the same way you did in a flat plane wiring scheme. So what we decided to do is employ the same technique. So these are our power stations. What you see is this is power station 1. This is the one that has the control booster in it, and also has an industrial area. So what you see is this panel here has the boosters. These are the circuit breakers. These are those switches, the DCC relays. These are the on-off switches. These are the connections to the layout. And then this is, and I apologize for the wire hanging down there. This was while we were working on some stuff. This is actually the detector panel that sits next to that. One of the things you'll notice is that all of these panels on the back have a cover that says do not open 110 volt power inside, because we do have 110 volt power inside of these. And by the way, you can see the DC supply here on the side, and this is the DC distribution wiring. So the idea is if you want to do DC, instead of doing what people were doing was putting a wall wart in, which somebody has to remember to unplug, you now just connect to the DC power for lighting for a building, and automatically it turns off when you turn the layout off. This is the one that's under the mountain. This is the detector panel, which is actually across the aisle from this unit. And this is that back corner. And we decided to put because of both space limitations, we decided to put the detectors into the fascia here. Actually was hoping they would be more visible from the aisle so we could talk about it. But it turns out unless you're 6'6", they're not really visible. But again, this is then that power panel for that area. And you'll notice we only have to have 3 circuit breakers there. We just don't have enough track there to demand a 4 circuit breaker. So basically, this is what they look like getting built. You see, this is the 3rd panel. This is the panel number 1. All the components are mounted on the face, and all the wiring, you'll notice, goes through the face into the back. And I'll show you that in a moment. This is one of the detector panels being wired. This is a little bit about what's in the power station. So we talked about this before, but you'll see at the bottom you have the transformers for the boosters. You have the boosters at the bottom. You have the circuit, then that feeds to the circuit breakers. They feed to the DC, but and up to the switches that control each of the tracks. Very nice, by the way, for troubleshooting. So if you've got a short, you can flip the switch off. If the short clears, you know the short is out in the track wiring, not in something problematic in the panel. And then we have here the master power switch. You'll see that it's normal off and on, so you can control the power there. And then these are the connections up to the layout up here. We've also got a cooling fan back here, and we've got space down here. This was taken, this is the main panel. It's got the space for the command station, another booster for our industrial area, and then we've got a GMRI Pi, a Raspberry Pi that's running GMRI that does our Wi-Fi and does some other stuff, functions for the layout. So this is what it looks like inside. So if you look in the back, what we've done is all the wires come into the back. And basically what they do is, we start at the bottom here, and you'll notice that these are the wires from the circuit breakers or from the boosters. And you notice they go through some of those clamp down connectors, and then those separate the signals to go in here to the circuit breakers. Then the output of the circuit breaker goes to the DC relay. That also gets the DC, which actually comes from up here. The output of the relay then goes up to this switch with the light, and then that goes up to the output. So the beauty of this is that all this wiring is hidden. You don't ever see it, and it can be relatively clean, and it's in a space that's very open, so it's easy to wire. So these are the other two power stations. I just leave these here if anybody's interested. It's basically the same set of components in that. By the way, the reason these drawings are here is these are all part of that PDF I talked about that basically describes in detail. And the idea is if at some point in the future, the members have to go maintain this and I'm not around or other folks aren't around, wanted to have a way that was pretty easy to understand what was there and how it was wired. So we had a decision to make. We started with this plan of doing a 1961 CTC panel. In fact, I started, if you look right here in the middle where all these green blocks are, this track, I started cutting the blocks up to match that CTC plan. So this was originally 3 blocks and became, as you can see, about 9 blocks. And we had that problem show up with the issues with the DCC operation because of the wire distance. And we made a very rapid fire decision that cutting the rest of the layout up into the 120 blocks for the CTC was going to be a huge amount of effort, a huge amount of rewiring. So we made a decision to take an immediate step to rewire the whole layout into the power stations using the existing blocks. So these are the existing blocks we have around the layout, including those new blocks that were cut there. And what you see is how each one is wired. And you'll see in a moment that becomes important because those are all documented and how they tie into each detector, which is incredibly important when you get to troubleshooting. So from a wiring perspective, we had to make a choice on wiring and did some investigation. And one of the things they tell you in DCC is you want to twist your wires so the wires are close together. There's really 2 reasons for that. One is noise in the DCC system, but the other is actually almost more interesting. It turns out that the DCC waveforms actually are in the area of AM radio. And if you put a big DCC wiring system in and you have the wires a long distance apart, it ends up looking like a big dipole antenna. And you end up throwing a lot of noise out because of the dipole antenna. So they recommend, generally it's recommended best practice to twist your wires for DCC. It turns out there's a pre-twisted wire, which is called zip cable. You guys know this all from the wiring you get on a layup, but more importantly, it's used for stereo wiring because it turns out the same exact things apply in a stereo from a noise perspective, that you want the wires close together when you transmit the signal off to your speakers. So what we found is this Chinese 12-gauge speaker wire you see there on the right. It's actually a zip cable. You can see that it's a black and red wire. They're actually molded together. It's Chinese 12-gauge, which is equivalent to American 14-gauge. Never understood how you have different wire gauges on different continents, but that's essentially what it is. We bought this stuff. It's a company called Install Gear. I think last time I looked, that 250-foot spool was about $60. So it's actually very reasonable. It is copper coated aluminum wire. So it does not have quite as much current capacity as copper, but because we limit all of these to 8.89 amps with the circuit breakers, we weren't concerned about the current carrying capacity at the distance we were talking about, which is about 30 feet maximum. The other thing we did was we used Wago lever connectors. These are actually available at Home Depot, at Lowe's. Basically, these are really cool. They handle from about a 12 gauge. They may even handle a 10 gauge, but I know they handle 12 gauge wires all the way down to 22, 24 gauge wire. And what you basically do is you open that little clamp, that little orange thing opens as a lever. You slide the wire in, you close the clamp, and it clamps down on it. This has two absolutely huge advantages for wiring versus soldering. The first is you're not soldering under the layout and dripping solder on yourself, which I find to be somewhat untenable. The second is if you have issues and shorts, it's easy to disconnect wires and to isolate the short. Quite frankly, the benefit, one of the nice things about soldering is you can have a bus wire and wrap wires around it. You really can't do that with this. But what we found is for what we were doing, which we were wiring the existing blocks that were in place. So the 10 feet on the layout where there was a bus, where there were feeders to it, we retained that piece of wire, and then we would cut that and tie in with this new wire back to the detector for that block. We also at the same time chose a 14 gauge zip cable for our 12-volt distribution wire that's blue and brown. So one of the things we wanted to start doing, we had a layout that someone had donated a whole bunch of black wire, 12 gauge wire 40 years ago, and they used that wire for almost everything. So there was no way of telling when you got into the layout what a wire was. You couldn't even, not only couldn't tell where it went, where it came from, you had no idea what kind of signal and really what it meant. So we now have this 12-volt distribution that's good for about 12 amps. And again, we use Wagos and screw terminals for the distribution of that. So generally now, if you want to do something, if you're going to say light a building, what you can do is look around into the layout, find that 12-volt wire, and just run to the 12-volt wire for your building lighting. So the detectors we put in enough detector blocks and in the right locations for that SP CTC plan. So this is just an example of what the detectors look like. So this is actually the front panel. What you see is in block A and block B on the main line, there are not a lot of blocks there. PS1 detectors that are on block A, there are only 4 blocks in this area that are covered, and there are only 3 blocks on the B side. These blocks here are all those blocks in that area that I cut in to actually make it match the CTC plan. And then these blocks over here, these detectors actually feed our yard. They feed the yard panel, the yard feed, and the runaround. And the nice thing about that, again, is if you have a short in the yard, it's easy to identify where it is. What we've done is to make this easy, we put detector assignments together for each of these so that you can go in and very easy to go in and see which one each is. And you'll notice all the wiring is labeled. These are shrink wrap labels that you actually print and you shrink wrap onto the wire. So all the wires are labeled at both ends as to what they are, so it's easy to find them. So these are the other 2 detector panels. This is the one in the back under the mountain. There's a 4th detector block there that's separate that I didn't take a picture of here. And then these were actually built into the fascia. Thought that would again be nice. So one of the nice things we got done with all this is in the DCC troubleshooting process has become a lot easier. So for example, if you have a DCC issue, if something stops, you'll know the area it stopped in. You go look at the power panel, you can see it from the aisle. And what you'll see is what you see in step 1 here. You'll notice there are 3 circuit breakers. The one in the middle looks different here. That's because when this light comes on, there's a short circuit. Once you see that, you can now use the switch above to switch it on and off to see. So basically, this will be off, the light will be off. When you switch this off, the light will stay off, but the short circuit right below will clear. That tells you the problem is out in the layout. Then the next thing you can do is go to the detectors. Again, notice these are all labeled PS1, PS3. This is PS3. You can go actually remove detector cards until the short goes away. And now you know which block it is in specifically. So it becomes really easy to kind of do this remote troubleshooting. So one of the things we did was we wrote up a fairly lengthy manual of operations. It has a lot of the things that are on these slides. You can see in there the layout of each of the panels. You can download it either using the tiny URL or the QR code. So that's all, folks. And again, I'll put that up that if anybody's interested. And that's it. So is that interesting? Probably for a lot of people, it doesn't really matter that much. You want to put it back up, Frank? Did you get it? Probably not of a lot of interest, but for some of you like Frank who've gone totally dead rail, this whole DCC stuff is now an anachronism. But it was a good project. We've been in an operational mode for about a year, and we've literally every problem we've had has been I will call it, for lack of a better word, a human problem. So, for example, someone in the yard running a locomotive past the break in the yard between the turnouts, so they short out the turnout. And again, it's really easy to find that by going through and figuring out exactly which of the blocks is actually being shorted. So with that, I will conclude and throw it back to everyone else to do some coast modeling or commentary.
Good clinic, Phil. Thank you.
Thanks, appreciate it. Well, it's been an interesting journey for the club to get, but it seems like we've reached pretty good stability where, unfortunately, I live about 5 minutes away from the fairgrounds, and so for a period of time, I was getting regular calls. If I didn't go in the morning, we had a show, I'd get a call at 8:30, 9 o'clock saying, "Hey, we've got a problem here. Can you come down and do something?" And quite frankly, that's really stopped. It's actually been very reliable now. So, and that's important when you have a public facing layout. The club in Pleasanton this year will probably have almost 60,000 visitors. And that puts it probably in the top 5 model railroads in the United States. Definitely places like San Diego and Chicago, the Museum of Industry have more people visiting. But I saw a thing about Greeley, and I think Greeley said they had 20,000 visitors. So and people don't come to visit a model railroad; they come to go to the fair, they come to go to the train show, and they happen to see a model railroad while they're there. So it's kind of important to have it work well.
Hey, Phil, I want a great presentation. I would love to look at more of those pictures in detail. And so I would love you to post it as you usually do.
Well, actually, both, but if you look the QR codes, both the presentation is available as a PDF, but the document is available as a PDF as well. It's a here, let's see if I can probably pull it up here. Take me a second.
Could you link it in the chat for us?
Yeah, I can. Absolutely.
Yeah, that'd help. I don't have my phone with me, so
hang on. Let me throw it. I'll throw it in the chat. That's the easy way to do it. So first I'm going to put in the chat is this is the presentation. And then this is And that's the document.
Hmm.
Here, I will. So I'll throw this up here so you guys can see. This is basically what, one of the things, again, we wanted to do was to make it so that you could, actually troubleshoot it. So, if you look at it, this is basically what that document looks like. I mean, it's got a whole bunch about the basic design. Most of the pictures that were in this presentation came right out of the document. So it's basically the same information in a lot of ways. And so it's got all of those, and then it's got, a lot more detail on all of the, the detector assignments and, how each one's laid out. And then the last part is the troubleshooting. So yeah, so that's a PDF up there. And by the way, that's something I would highly encourage everyone to do. We're rewiring our turnouts, and we're going to do the same thing, write a manual for that. I think if you're a club and you don't have some manuals like that, ask the people that do a project or write a manual, because that knowledge becomes tribal. And it's amazing how many times you ask a question and it's like, well, so and so did that, and we don't know exactly what he did. So, enough said.
You won't even remember what you did, Phil. You got to write it all down.
That's true. That's true. You don't remember it all.
Great
Anyway,
job, Phil.
Thanks.
Thank you for watching this Coast Division eClinic. More Coast eClinics can be found on the Coast Division YouTube channel.